I think people are still underestimating the importance of this thing. If there's a chance it's real, which I'll say publicly kind of for the first time, I would put it around 10% or something. Like, I don't think it's going to turn out, but there is a chance it's real. This would be like the most important physics discovery of our lifetime by far. I think that it's still highly undervalued and under discussed how important this thing could be. It's a topic, room temperature superconductors. You may have heard about it in like a science class documentary in eighth grade to get you excited. Or if you like took an introductory physics seminar at college, there's like, these are the big open problems in physics we want to solve. This is one. This is like really the holy grail that I think we should all be chasing after. It's been interesting to see, a lot of the skepticism, a lot of the kind of tamping down of enthusiasm and excitement. Instead, I think we should use this opportunity to get everyone saying, like, guys, we should put a lot of effort behind finding something like this. Even if this one's not it, it would be really, really impactful if we could find it.
Alex, thanks for joining us.
Thanks so much for having me.
Do you want to briefly introduce why you're here?
So about 10 days ago, I tweeted a thread about a new physics paper on the archive called The World's First Room Temperature Ambient Pressure Superconductor. And I got people really excited about what would happen if it was true. Everything from nuclear fusion to quantum computing, as well as some quotes from the paper itself. And since then, 30 million people have viewed that thread. It kind of took over the internet. And I have like 40,000 Twitter followers, up from 200 11 days ago. And kicked off a lot of interesting conversation about superconductors, room temperature superconductors, and a lot of drama and gossip about this paper and replication efforts. So it's been a fun ride on the Twitterverse, or X as it's now called. And I'm excited to chat about that paper, about the implications, and hopefully some things that aren't yet public and widely known.
Okay, so Alex, before we hop in, just to kind of give the people who want an answer, do you feel like the paper has been replicated at this point? Or if you were to grade down on a scale of 1 to 10?
I hate to break it to you. No one has proven that LK-99 is a room temperature superconductor yet. We have a lot of interesting data. And as one physics professor put it, interesting in many of the right ways. But there is no proof yet that LK-99 is a superconductor. What you'd look for proof is a really clear phase transition from an insulator or a conductor into a superconductor, where you have a graph that shows some resistance and it goes from some positive value to basically zero at a certain point. Look for this sharp drop. It's a hallmark of superconductors. It was the first way a superconductor was ever discovered in 1911, as well as there's a lot of other measurements you can make. But that's the surest one. We haven't seen anything really close to that yet. And no one's convinced that it's real yet.
I mean, I know we could get into some of the drama around why this was published the way it was published and kind of the lack of details. But the thing that I haven't been able to piece together, because I live in a world of bits, not atoms, is, so in theory, you have this paper and it says, this is what we did to kind of go create this thing. And then, you kind of have the guy at Varda who, a lot of this stuff seems to be happening outside the US, but at least we got like one English language version. I know Iris was doing stuff from her home furnace. But the thing that I don't quite understand is, why isn't it kind of like just like baking a cake, right? It's like you follow the recipe, put it in the oven, and then it pops out, and then you have it. So like, I'm very naive in that sense. So maybe educate me a little bit on why is it so difficult to replicate this material?
Yeah. So in order to fully understand it, I think it's interesting to talk a little bit about the chemistry and physics of crystals. So indulge me for a second or so. Any material with a regularly structured lattice of atoms is called a crystal in physics. And crystals have interesting properties in that they can share electrons between atoms. The electrons can flow in different paths in the crystals. And when you're making them, either default by chemistry, by what's most energetically favorable, or via some fancy technique, you have certain arrangements of atoms that contribute to the crystal structure. So the current, confirmed highest temperature superconductor are called these cuprate crystals, which are copper oxide crystals, usually have some kind of rare earth element like yttrium, and then barium, and copper, and oxygen. And these are very carefully ordered and structured so that the electronic bands, or the places where the electron is allowed to flow, can be a super smooth and kind of clean path through this crystal at the right temperature. That's a little bit of an oversimplification, but what it gets at is The ordering of the atoms in this crystal is extremely important for the electronic properties, how the electrons can flow through this material. And what we currently think is probably the case with LK-99. It's a crystal based on lead apatite, which is a lead and sulfate kind of crystal, where you move some of the lead atoms and replace them with copper atoms. Now, the challenging thing is it's very hard to choose which lead atoms you're going to replace with copper atoms if you just grind them in a bowl and blast it in a furnace. And some computational calculations have showed that the version of LK-99 that's most likely to be superconducting has certain lead atoms replaced with copper atoms, but the less likely or less energetically favorable lead atoms are the ones that are supposed to be replaced. So you're kind of working against nature when you melt the copper into this lead in a process called doping. You add some free electrons from the copper, you replace some of the lead atoms. And unfortunately, if you just did it kind of by chance, you'd get very few lead atoms correctly replaced with the copper, at least what we think would be the right configuration, because it's the less energetically favorable lead atom that you need to replace to get the right structure. So that's a little bit as to why the synthesis may be harder than we initially thought. If you looked at the initial paper, it was like 3 steps. Just melt some apatite, add some copper, grind it up, put it in an oven, and like you'll get a superconductor. So that's why I got really excited initially. It's like, wow, we could go do this. It's looking like it may be harder to produce than we initially thought.
But to the point where if you do get it in the right structure, some of these interesting properties seem to be showing up, like, and maybe to explain the different things that people are observing, like the floating rock is the meme. And I see this term diamagnetism, and it's like people are like, oh, this is just diamagnetism, this is not superconductor. Like, maybe explain a little bit of that, like, because clearly some of the fragments of whatever people are making are exhibiting weird or kind of interesting properties.
So, one of the hallmarks of superconductors is that they float in a magnetic field. Because the electrons can flow with zero resistance, they tend to form currents in the superconductor that oppose the magnetic field and allow it to float freely. So, there's some superconducting maglev trains that use this property, or you may see some cool videos of like a little puck of a superconductor going along a track of magnets. It's called the Meissner effect, and it's really a hallmark of superconductors. On the other hand, there are other materials that oppose magnetic fields that we broadly classify as diamagnetic. So a material can be paramagnetic, ferromagnetic, or diamagnetic, and that refers to how it responds in a magnetic field. A ferromagnetic material is magnetic by itself, like it's a magnet, whereas paramagnetic can be magnetized. The diamagnetic materials, on the other hand, are those that naturally oppose magnetic fields because of how the electrons interact with magnetic fields in that bulk configuration in that material. So we have some examples of diamagnetism in nature. For example, bismuth is naturally somewhat diamagnetic. If you put it next to a magnet, it kind of pushes away and floats away. But recently, we've developed more and more materials that exhibit diamagnetic properties. One of them is called pyrolytic graphite. And you can see pictures of graphite, pencil lead, that's treated in a certain way, floating on top of magnets. And that's pretty cool. So we've seen pictures of samples that have claimed to be LK-99 floating on magnets. There's 2 possible explanations, basically. One is that it's diamagnetic, and the second is that it's a superconductor. These aren't necessarily either or. There are a class of superconductors called type 1 superconductors that are moderately diamagnetic. They don't perfectly float, but they do repel magnetic fields. And then type 2 superconductors can float perfectly in a phenomenon called flux pinning, where it just stays in the exact same place, never wobbles or anything. It's also called quantum locking. So it could just be that it's a non-superconducting diamagnetic material, or it could be a superconducting diamagnetic material that opposes magnetic fields. What I'm not convinced we've seen yet is super strong flux pinning, where that thing is stuck in place. It won't wobble at all. And that's you can see videos of yttrium, barium, copper oxide, cuprate superconductors that are just totally rock solid. You can move the magnets and it stays in the exact same place. But that's a little bit on diamagnetism versus superconductivity. Not necessarily exclusive, but interesting phenomenon.
So if I was to kind of play that back, what we're seeing now in some of these results in internet videos, maybe because they haven't been tested in the physics lab or kind of formally verified by a bunch of different expert types, but the LK-99 process that people are trying to replicate are creating materials that do start to have some of these properties, but no one has actually been able to tie everything together, right? So the Meissner effect stuff plus the actual phase shift you were saying around temperature, or not temperature, the conductivity.
Resistivity. Yeah. So, I mean, the main property of a superconductor is it should conduct electricity with zero resistance. And we haven't really seen a convincing graph that shows that it conducts electricity with zero resistance. Most of the data we've seen is very noisy and shows that it could have some resistance, but the materials and instruments aren't precise enough to measure it yet. But floating rocks are a pretty big deal because, like, it's pretty hard to make a diamagnetic material. And I think the only reason people are taking this result seriously in the first place is it came out with this picture and video of a floating sample of something. And that's really remarkable. It's pretty rare to find new diamagnetic materials, and they're pretty interesting. And to do that in a claimed superconductor is above and beyond a lot of the recent discoveries of claimed superconductors. We really haven't seen a lot of pictures of them floating like we have for this one.
With material science like this, is it a lot of just trial and error? Like, how do people even come up with new materials? And is it happening in academic labs? Is it happening kind of in industrial processes? Like, I don't even, like, how do you even go invent a new material?
Yeah, that's a great question. There's so many ways you could do it. Right now, a lot happens via computer simulation, where you try to model what some interesting properties that you're looking for are, and then come up with what materials might fit those configurations. So, superconductivity has been a holy grail of physics for 100 years or so at room temperature and ambient pressure because of its implications for power generation and so many things you could do with it. And so that's been a subject of a lot of study is computational modeling of superconducting systems. We have some theoretical understanding of how they work, but we don't have a great understanding, I would say, of all of the interactions happening within a superconductor and what are some of the key criteria that would allow it to superconduct at higher temperatures. So in material science in general, a lot of it, in industry and things will come from we need a material for a specific use case. Probably the canonical example are the millions of different types of plastics that we have that have different properties where you can adjust them one way or the other in order to make them bendier or firmer or thicker, more insulating. But there's obviously a lot of different materials that we work with. Usually start with the properties that you're looking for and then kind of do an overview of what are some similar materials, how can we improve on them, whether it's by doping it, for electronic properties to add more electrons into it, or changing some of its parameters like its strength or elasticity, insulating properties. And one interesting parable here is when we first discovered these cuprate superconductors, they were extremely brittle, extremely hard to make, and they didn't work very well. And there were only tiny parts of the sample that usually ended up being superconducting. But since they were initially discovered, we've pushed their critical temperature from what I think was initially 40 degrees Kelvin when they were first discovered, now all the way up to 100 degrees Kelvin, as well as improving on the synthesis process, their purity, and their use cases. And now you see a lot of these cuprates used in some really cool physics experiments like fusion systems, like Commonwealth Fusion uses tapes of them in order to try to create nuclear fusion. So I'm optimistic we can improve LK-99, but yeah, there's a lot that goes into material science broadly.
And maybe for our audience, maybe explain why going from 40 Kelvin to over 100 Kelvin, A, why are you using Kelvin as the measurement? And then B, like, why is it going up being good?
So the really important thing with this first cuprate superconductor is it crossed the threshold of the temperature of liquid nitrogen. I don't know off the top of my head, but my dad once told me that liquid nitrogen is about the same price as milk. So it's a lot cheaper than liquid helium or other ways to cool things. And if you can just get a giant tank of liquid nitrogen, it's a lot more economical to run your superconductors with that than other, much more expensive ways of cooling like liquid helium, which are only a few degrees Kelvin. The Kelvin scale is useful for this because, most superconductors superconduct at just a few degrees Kelvin, very far away from our room temperature, like 300 Kelvin.
I do want to get to the like trace the drama a little bit. Like what's the evolution here?
Yeah, it's a really weird story. I mean, you have to think that there's something sketchy going on when two papers appear on the same day. Both of them are written with typos, claiming to have found the holy grail of physics. They don't have the same authors list. And in fact, one of them only has 3 authors, which implies that one of the authors thinks that they're going for a Nobel Prize, which can only be split amongst 3 people. And both of them have these totally nonsensical charts that really don't make any sense, measurements that are done in very non-traditional ways, and a claim of this superconducting material that's potentially very easy to make. So a really weird set of facts to start with. Also, no one had ever heard of these physicists. They weren't affiliated with the university. They came super far out of left field. And so you can be sure that every respected scientist, when they saw this, kind of shrugged it off. There's been lots of claims of materials like this that have been superconducting, and almost all of them have turned out to not be replicated in research laboratories.
Hey, we'll continue our interview in a moment after a word from our sponsors. Hey, everybody. If you're a business owner or founder like me, you'll want to know more about our sponsor, NetSuite. NetSuite provides financial software for all your businesses. Whether you're looking for an ERP tool or accounting software, NetSuite gives you the visibility and control you need to make better decisions faster. And for the first time in NetSuite's 25 years as the #1 cloud financial system, you can defer payments of a full NetSuite implementation for 6 months. That's no payment and no interest for 6 months. And you can take advantage of the special financing offered today. NetSuite is #1 because they give your business everything you need in real time, all in one place to reduce manual processes, boost efficiency, build forecasts, and increase productivity across every department. More than 36,000 companies have already upgraded to NetSuite, gaining visibility and control over their financials, inventory, HR, e-commerce, and more. If you've been checking out NetSuite already, then you know this deal is unprecedented. No interest, no payments. So take advantage of the special financing offer with our promo code at netsuite.com/Zen. That's netsuite.com/Zen to get the visibility and control your business needs to weather any storm. netsuite.com/Zen.
At the same time, scientific discoveries often come from very unexpected places. And I think it's worth being open minded that researchers who are working outside of a traditional lab or traditional model may take a novel approach. A lot of superconducting research is about marginal improvements to current QP rates rather than really throwing random stuff at the wall to see what sticks. So you have to have some prior that there's a chance that if we did discover a room temperature superconductor, it might come from a very odd place in a very odd format. The drama between these authors, the publication, the papers is very odd. It seems like the two main authors, Lee and Kim, whose initials make up LK, initially found some signs of superconductivity in 1999 with some form of this, copper doped lead apatite crystal. So they named the material LK-99 and tried to work on it for a while, but couldn't really get any clear results that would be worth publishing. So one of them went off to work in a battery lab. The other languished as a postdoc who never got an offer for professorship and just languished in various labs until I think it was a few years ago. Kwon, who's one of the third authors, got funding from some external private party in order to commercialize this technology, restart some research. Then during COVID, Lee and Kim seemed to have just shut themselves away in a lab and made thousands and thousands of these samples to try to find the signs of superconductivity. There's some comment that the sample that they showed in the paper was number 1,500 or something that they've been making. And in this total obscurity, they'd been languishing, just making these materials and finding things that they thought were really interesting. They partnered with United States based Korean physicist Hyun-Tak Kim, who's at the College of William and Mary in Virginia, in order to try to shepherd some of their results through the prestigious United States academic publishing system. And then it sounds like, for some reason, the Korean Kwon, who the third author brought in to help shepherd it and get funding, was fired from their research project in April and then went off on his own, wrote up his results in a paper. He added Lee and Kim as co-authors and put it on the archive to try to get some press for himself and tell the world about this. As soon as Hyun-Tak Kim at William and Mary saw this, he was like, oh crap, we have to get our own paper out there. A few hours later, published his own paper to the archive that didn't have Kwon as a co-author and had some different graphs and different findings as well. And since then, there's been a lot of feuding between them. They're all very skeptical of the scientific establishment and not really collaborating closely with other researchers. But Hyun-Tak Kim at the College of William and Mary, at least, has been on the phone trying to help labs replicate it and really does believe that this is real. So there's a lot of intrigue here, a lot of really weird things, and it's coming from weird angles. To make the story even crazier, as you were saying, Dan, there's people just doing this in their kitchens, trying to make this material, tweets of unverified floating rocks coming from all over the world. So it's a very dramatic story that has been very fun to follow along live as it's happening.
I happen to be an investor in Varda, and so I know one of the co-founders there pretty well. And he kind of, quote tweeted or quote X'd or whatever they call it now. One of the employees is saying, well, I have to go try to replicate this. And so similar to your story in terms of going kind of from nobody on Twitter to now all of a sudden 60, 70, 80,000 followers, I forget his name, is Andrew, I think.
Andrew McCallum. Yeah.
Yeah, he just became kind of overnight the call it English language version of the internet person outside of this anime character Iris, who I guess is a real scientist like that people know of, but maybe is just kind of under this anonymous account. But they were kind of going back and forth while one is sleeping, one is kind of taking up the mantle of trying to do the replication.
Yeah, it's pretty cool. I mean, I think it's great for science to be democratized, for people to try this themselves. I think that Andrew and Iris are probably very good scientists, and it might be harder if you're doing it in your oven at home. You know, they have some really professional material and years of experience in material synthesis that is under the hood helping a lot of their experiments come out better than ours would be. But I think it's awesome for science to be democratized like this, for there to be like live tweets about replication efforts and the whole world's watching superconductivity. Twitter has been awash with many stories that I don't think really benefit the public conversation, whether it's like a latest political scandal or the Elon Zuck cage match or something. And for us all to be so excited about like potentially the most world changing technology out there, I think is a great thing for us to focus on and talk about.
Yeah, I think it's an interesting characteristic of Twitter, and it's a bit of a Rorschach test in that if you don't like the raw stream of most stuff could potentially be fake or it's like low signal, like a lot of FUD. I think there's a certain type of person on the internet that thrives with that. It's like, oh, it's almost like you're kind of trying to piece together what is actually true. And maybe if you're the type that likes to get it in the newspaper the next morning with a stamp of approval, like that just sounds awful. But I work in crypto, and crypto, when SBF was blowing up last year, the big joke is that you kind of have all these autists and CISO type folks who are on the blockchain piecing together all of these kind of movement of funds, and I just think that is uniquely enabled by something like Twitter, where you get this real timeness and easy kind of virality that can spread, and people to be able to add their context on top of whatever's happening. I think the establishment doesn't like that because you're outside of the control, right? And now any expert, and this happened also with COVID, right?
Yeah, I mean, the citizen journalist aspect of this is super strong and interesting. The other thing that I've learned from being now one of the Twitter voices is the barrier to entry to pointing out things no one has noticed is extremely low. And most of the people reporting on this stuff are no more experts than any one of us. And if you can read a paper and look at a graph and really like think about it for a second or two, you can be as genuine a participant and voice in the conversation as anyone. There's one graph in one of the initial papers that everyone said was a phase change in resistivity. Like random Twitter account pointed out, actually, this line is less conductivity, or is worse at conducting. It's more resistive than copper. So very common, conductor. And so it's like literally more resistive than copper, and people are claiming it's a superconductor. If you just looked at it and thought about it for a few seconds, almost anyone could have come to that conclusion. So it's been very enlightening to me to understand that you really can, I think, be as genuine and interesting a voice as anyone if you just do the reading and look into it, do some research, etc.
Well, it's the classic thing where the quickest way to find truth is just post something on the internet that people point out is wrong, right? And
Yeah.
and it is kind of interesting to think that stuff that has to live through the truth seeking nature of Twitter with all of the kind of distributed set of people, rather than going through maybe a little bit more Byzantine and kind of closed process for peer review. I don't know. I think it's a pretty special property.
Yeah, and the other dynamic of this story is so many of the mainstream science journalists just have like disdain for the people on Twitter getting excited and pointing things out, and it's really weird how they don't like all of this excitement and enthusiasm, and they're like, everyone calm down, this is irresponsible to say that something important has happened here when we don't know all the facts yet. But living in that like exciting interlude, I think, is totally fine, and it's cool to get excited and care about it. And there's a lot of kind of patronizing from the establishment class of science journalists that I think is interesting to see firsthand as well.
Well, the one that was really striking for me is I wake up usually and I check Twitter and I check Tech Meme, which kind of the front page of tech news. And the front story that had just popped up onto Tech Meme was a Nature article talking about how LK-99, the results, have been not fruitful from a replication standpoint. And then the contrast was, as I went to Twitter, I had a very clear video from Andrew at Varda where I don't think he's claiming that it is a superconductor, but he's showing off the kind of floating rock in a very clear way, right? Like no more grainy photos that kind of like, okay, why didn't you just like post a video like we have modern cell phone cameras? And so it just felt like such a kind of like the establishment wants to bless something versus kind of like the internet is saying like, hey, here's something cool I did. Maybe someone else can take it from here.
And the great part of this story is there's something tangible at the end of the day that like shows who wins. Like if you get a graph of resistivity, it doesn't matter if it comes from some super fancy $1 billion established lab or from your garage. Like if you find the truth first, you can actually be the voice and the proof in the conversation.
That's in theory what science is, right?
Yeah, yeah. But like, you know, at least in this case, we have all these gatekeepers trying to keep people out from the conversation. But if you can prove it, you know, then your results speak for themselves.
What's the difference here between physics and chemistry? Because from a layman's standpoint, I always think of physics as being much more theoretical, and chemistry as kind of being the applied aspect of physics, right? And then chemistry is what builds you up to biology. But maybe for again an ignorant person here, where is that kind of phase change from a scientific standpoint?
So the field of physics we're talking about has this insane name. It's called condensed matter physics, which is a ridiculous way to describe just like actual things you can touch.
The third co-host of At Moment of Zen was a dropout from a PhD program at Berkeley on condensed matter physics, but he decided to not show up at the podcast today because he had some other conflict. So we'll save it for another time.
Last minute bailing. And if the audience wants to hear more of Antonio, just constantly shame him.
Yeah, shame him on Twitter, shame him on YouTube. Condensed matter physics dropout, and he didn't show up to the conversation.
Well, it would have been cool to have him on, and I can't wait to hear what he thinks as well about the whole LK-99 saga. But so there's not really a sharp line. You know, chemists are very interested in the interactions between atoms and molecules, different energy levels, different states that you can grow, and there have been a lot of great I think contributions from chemistry professors as to whether this crystal structure is actually stable or not, based on the configuration of atoms and electronic properties. Physicists on the whole, try to, I think about systems a little bit more abstractly or like another layer of either abstraction or in depth. So it's very common to, for example, physicists will describe the shape of electronic orbitals for an atom, your s orbital, your p orbital. That's a quantum mechanics problem. And then once you have it, as a chemist, you can piece together how two atoms with different orbitals will interact, whether or not they'll form an ionic bond or a covalent bond. But there's a lot of overlap, especially in something like this, where you're worried about how do we make this type of crystal? What are its properties?
So arguably, going back to this idea of trying to get the right amount of copper and lead balance and the right switching of atoms, there could be a version where now some world-class chemist is looking at this going, oh, interesting, well, I might use this technique, or I've done this in some other area and I get a little bit more precise. And so the applied manufacture of this material could actually be a chemical breakthrough.
Absolutely. I mean, there's many layers of different expertise that'll be important if we ever get close to trying to commercialize something like this. I think chemists have already suggested, could we, for example, use gold instead of copper to dope the matrix? Would that be more stable and be a little bit easier to get in to the lead apatite? So a lot of, I think, interesting contributions from chemists. Physicists are mostly here to try to figure out, is this material superconducting? If so, why would that be? What are the properties of electrons in this material that would lead to that? And once they kind of have a yes or no, they probably hand it off to a bunch of chemists to figure out the right way to manufacture this material, and then a whole supply chain of machinists and computational chemists and things like that who would actually commercialize something like this.
Can we do an aside on one of the chemicals that ingredients that are required here? So something like red phosphorus.
Yeah.
And so this is a chemical that's also used to make meth, and that's why it's controlled. And like I think Andrew was having a hard time getting access to this.
Yeah, it is pretty funny. So the initial paper, I think they had to synthesize their own lead phosphorus, Lee and Kim, because they were having trouble buying it as well. But red phosphorus, I think, is 3 copper and a phosphorus. And it's how you can get your copper doped into the lead apatite in a way where, so the lead apatite has phosphates, PO4s, in the material. And so in theory, I don't understand this part that well, but if you have the copper and phosphorus already bound, then it's easier for the copper to make its way into the lattice when it's doping, rather than just like melting it with a pot of copper or something.
Alex, what are questions that you are most excited to figure out over time? Like, what's Yeah, what are the biggest things kind of on your mind?
I think people are still underestimating the importance of this thing. If there's a chance it's real, which I'll say publicly kind of for the first time, I would put it around 10% or something. Like, I don't think it's going to turn out, but there is a chance it's real. This would be like the most important physics discovery of our lifetime by far. I think that it's still highly undervalued and under discussed how important this thing could be. It's a topic, room temperature superconductors. You may have heard about it in like a science class documentary in eighth grade to get you excited. Or if you like took an introductory physics seminar at college, there's like, these are the big open problems in physics we want to solve. This is one. This is like really the holy grail that I think we should all be chasing after. It's been interesting to see, a lot of the skepticism, a lot of the kind of tamping down of enthusiasm and excitement. Instead, I think we should use this opportunity to get everyone saying, like, guys, we should put a lot of effort behind finding something like this. Even if this one's not it, it would be really, really impactful if we could find it. And so that's, I think, a big under discussed thing right now, just more broadly in the conversation. There's, I think, other valuable, interesting physics and science questions with regards to this material. So the crystal structure is still not incredibly well understood. And I've been talking to some of the chemistry professors who are doing some analysis on different ways you could dope the copper into this. One of them is saying that there's basically no stable configuration of copper in the common synthesis of this apatite crystal. And he's working on a paper right now to kind of show, is it actually possible for there to be copper involved at all? Or is it that some of the properties may come from a different dopant, a contaminant of some kind? For example, both Iris and Andrew are considering whether red phosphorus sometimes has defects of sulfur that I think are due to its manufacturing process. And depending on which supplier you get your red phosphorus from, it can contain a little bit of sulfur. And one of the hypotheses is it actually the sulfur that's causing some kind of levitation rather than the copper itself? So I think those are some of the interesting science questions right now. Obviously, the main one is like, can we manufacture this material and get a resistivity plot? That's the one we're all trying to look for right now. But a lot of other interesting questions tangentially.
So from meth rocks to fart rocks, basically.
Exactly.
And so to your point, though, I do think it's worth kind of observing. Sometimes, especially now with the internet the way it is, to create a meme and capture the imagination of the world at a moment in time can actually have a powerful accelerating effect in terms of superconductors people knew about, but what are Silicon Valley billionaires who kind of instead of donating to the Red Cross or traditional charities, instead they build science companies. And so you could imagine someone who has a longer term horizon, who doesn't necessarily care about the academic establishments, put out a call to say, hey, I'm willing to fund material scientists or physics kind of people who don't care about being in a lab and really just want to search for superconductors. And long-term time horizon, you don't have to worry about where your next kind of chunk of funding comes from. It's like the mission of this institute is to get to room temperature superconductor. So I do think that's actually pretty powerful. And again, a testament to Twitter, in that you can create a global moment where people are getting excited about a pretty esoteric or hardcore version of science, right? Like, when was the last time people were this excited about science? Maybe the mRNA vaccines before, you got all the baggage associated with them.
I was talking to my brother about this. There's really only two tangible impacts of going super viral on Twitter, right? From this initial thread about LK-99. One is we got some more sales at Cometeer, which is the coffee startup I work at, from a lot of people clicking through my profile. And that was kind of cool. I love sharing the coffee with people. And the second is probably a lot of labs started working on this a lot faster than they would have otherwise. And a lot more labs did it. TBD if that's a good thing or a bad thing. Maybe this thing is not real and we shouldn't have spent the time. But it is interesting that public attention and enthusiasm can really spur a lot of work, especially in China right now. This has been the number one trending topic on Chinese social media for the past week and a half since the initial results came out. And almost every condensed matter lab in China is working on replication of some kind. So a lot of the kind of sketchy videos you see are from some Chinese like version of YouTube called Bilibili. But all of Chinese social media is like going crazy over this. So there's probably more enthusiasm, excitement, and work happening there. But it's cool to spur a little bit of that in the States as well.
One thing I wanted to shift back to, because you mentioned it, this idea of the glass tube, and then you kind of have to break it. Maybe explain a little bit, like, to the degree that you understand that, like what is that supposedly doing? And that doesn't seem very precise.
It's definitely not. If there's one thing that's clear, it's that Lee and Kim are not, I think, extremely precise scientists when it comes to making this material. I think it was Lee, who's the main kind of chemist of the pair, who gave a pretty long interview to Korean journalists about his process for discovering this thing. And a lot of it was like, look, I'm willing to put in more hours than anyone else, melting down lead in my lab. And people don't understand how hard the chemistry is here. And he was like bragging with a lot of bravado. And he clearly has some kind of chip on his shoulder from being shunned by the academic industry. But he had a few interesting tidbits. One of them was around like having thousands of samples that I think was interesting. And the other was the sample that worked. He noted in his lab book that he accidentally like took it out of the furnace and broke the quartz tube that it was annealing in on its way out of the furnace. There was a crack in it. And that sample, for some reason, ended up floating really well on the magnet, like way better than all the other ones. And he just had no idea why. And I don't really have a great idea why that would be either. Maybe there's some oxidization happening from like air entering the chamber or something. But it goes to show that the synthesis of this material is very poorly understood, even by the authors themselves. And so it's probably going to take some work to try to get something close to their samples and materials.
Alex, can you flesh out even more the world in which this is true? I know you said only 10% chance or something like that, but let's say it's true. Say more about what it means or what's unexpected about what the implications are.
This is a scenario where it's time to like dream really big. It's like something like the transistor coming, where we had thought of many use cases we could use transistors for. The obvious ones just being like repeating current, for a radio or something like that. But the actual implications on everyday life just blew out of the water anything we could imagine ex ante. And I think that's likely to be true. But we can go through what are the extremely obvious things we will put this to use right away. And then what are some things we might work on? And then what are like the big picture crazy ideas? So right now, superconductors are primarily used in MRI machines where they make very strong magnetic fields in order to look inside your body. MRI machines use liquid helium to cool their superconductors because the high temperature cuprates are very fragile and harder to make. So if you ever see an MRI machine, there's like these giant tanks of liquid helium sitting outside the room or like underneath the floor or something, which is very expensive and extremely cold and highly pressurized. And it actually used to break your iPhone if the liquid helium leaked and you had too much helium getting into your circuits, like caused some disruptions with the semiconductors. Anyways, that's a bit of a tangent. You can imagine all MRI machines would immediately switch over to using some cheaper, easier version of these room temperature superconductors. That's super obvious. The other way superconductors are used right now are mostly in, I don't want to call them physics experiments, but in physics research where you're trying to make very strong magnetic fields. Because you have no resistance, you can run so much current through this that you can make these super strong electromagnets. One, for example, is at the Large Hadron Collider in CERN, where you have these huge beams of protons being smashed into each other. These are the strongest magnets, like the largest, strongest magnets in the world for the most part. The other big one is, as we talked about, in nuclear fusion. So in fusion, you try to use these super strong magnetic fields to hold this plasma together so that the hydrogen, deuterium, tritium all collide with each other at very high temperatures and pressures and fuse together and make fusion reactions. One of the biggest challenges with fusion is creating that magnetic field, keeping it strong enough and tight enough to allow the reaction to replicate. And so that's why Commonwealth Fusion Systems, for example, is using these higher temperature superconductors, these cuprates, but ITER and the other big fusion collaborations all use liquid helium cooled traditional superconductors, which is really hard to use. You need these huge coils of liquid helium at 3 Kelvin, like 6 feet away from some of the hottest temperatures on Earth, millions of degrees Kelvin or something. And so that presents a huge challenge. And we would, I think, very quickly see a massive speed up in fusion research, which is the other big holy grail of physics, right? Can we make free electricity basically with just hydrogen, the universe's most abundant element? And superconductors unlock some major engineering update for fusion. So that would be really exciting. So those are the three, like you could immediately see it being used in MRI machines and fusion and then other kind of physics research, because that's where we use them right now.
Alex, maybe explain grid energy storage.
Yeah. So now it's like, what are some potential applications? Let's get more and more creative with it. So one that I'm most excited about is right now we're in this process of trying to decarbonize our electrical grid. We're trying to make electricity from low carbon sources and then use that on the grid for our end use cases. It's very challenging because most low carbon sources are very intermittent. The sun only shines, wind only blows at certain times. So there's kind of two things you can do here, and you probably have to do both of them. One is transmit a ton more electricity across the nation. so that when the sun is shining a lot in Arizona, we'll use it more in New York City. So building a huge transmission grid is a really key unlock for better decarbonization of the whole grid. The other is having a ton of energy storage. You need to just be able to store electricity after you produce it to use it later. So we have all these huge batteries coming online, lithium ion batteries or other types of battery technologies for different lengths, durations, and capacities of storage. Batteries are pretty hard to make, though. Lithium is, we don't have a ton of lithium active mines and refineries in the United States. We don't have a ton of battery manufacturing in the United States. And so one of the most exciting, I think, potential use cases for superconductors, and that we're actually doing right now on a research scale, are called superconducting magnetic energy storage systems, or SMES, where you basically just have a big coil of superconductor and you inject a current into it. Because there's no resistance, it just flows around the coil forever until you need it, which is pretty crazy. It does create a magnetic field in the middle because it's an electromagnet. And so you have to be kind of careful about your geometry. But you can just have these huge coils of superconductors that store electricity with zero losses for basically an indefinite amount of time. And then you can use that electricity and transmit it across the grid with superconducting wires to reduce all your losses. So the two kind of key challenges of decarbonization, I think, are key targets for superconductors as well.
So maybe to make this like a little bit more, I don't know if practical is the right term, but fantasy, if this exists, you could in theory put solar panels all over the Sahara or desert where there is no, put it in Nevada or somewhere. And now you can store all that energy until it's needed and then fire it across the United States and not have any loss. So from transmission always being the hard problem where it's like the sun is shining over here, but people live in the cloudy area over here.
Yeah. And energy really is the key input for economic growth, right? Over hundreds of years of industrialization, the more energy you use, the richer your society, the happier and healthier people are. And unlocking this much energy, be it through fusion, storage, transmission, is, I think, a massive implication for like GDP for our society, and is definitely, I think, the highest impact way you can use room temperature superconductor. But there's also a lot of other fun things you can speculate about, which are like, what are some crazy ideas we could do with superconductors if they ended up being real? One of them that I think we'd see a ton of research in is quantum computers. So right now, quantum computers use superconductors at very low temperatures to preserve coherence between different qubits. So you have these like entangled quantum particles that perform calculations. They need to be connected to each other with a superconductor. So you have to keep it really cold. Any small amount of heat will disrupt the whole system. Superconductors could allow you to make much more efficient quantum computers. You still need some kind of coldness for the qubits themselves, but a quantum computer with, I think, something like 5,000 calculating bits, you also need error correcting qubits, could run what's called Shor's algorithm, which basically, decrypts anything you need, steals all your Bitcoin, steals your bank account, breaks all of modern encryption by factoring prime numbers really efficiently with a quantum computer. And once we get Shor's algorithm, like the world looks very, very different. And so you can imagine one of these quantum computers coming out and really causing some major problems.
To be fair, the cryptocurrency people are actually at the forefront of making sure that the algorithms get upgraded both in Bitcoin and Ethereum to be quantum resistant. Whereas, SSL that's powering your Amazon shopping cart is that's not going to be in a good place.
I think in order to make your encryption algorithm quantum resistant, you need to have superconducting qubits that connect from the different nodes of the system in order to pass like quantum entangled information throughout the system. I think a lot of the research right now on quantum encryption requires you to literally run these huge cables of superconductors in order for the computers to connect to each other. I know there's some research at MIT going on right now, but it's safe to say we would probably decrypt things before we quantum encrypt them if we had a superconductor.
I'm going to have to go check with Vitalik on this because I'm pretty sure that they have a curve, and this is outside of my band, outside of that there is an elliptic curve or equivalent that is quantum resistant, but maybe I'm wrong.
Oh, that would be exciting. I don't know.
So one thing on the energy thing, maybe for the fans here, Kardashev scale, like this is like a physics thing.
It would be a major, major change to our society. A Kardashev scale civilization, I think refers to capturing all the energy from the sun or something. We probably don't need that much energy yet. What are the things that we need a lot of energy for? Probably like agriculture. We could do it all indoors with lights instead of depending on fickle weather. Desalination would be helpful. but it's tough to understand where we would use a billion times more energy than we're using right now or something. But it would be exciting. I mean, we certainly unlocks a lot more possibilities. Like you could have a railgun that launches your spaceships instead of using rockets. You could just have superconducting coils through a volcano, and it just shoots it up into the air with a super strong magnetic field. So maybe you could do more space exploration with that.
Maglev trains, transportation.
I mean, I don't think that high speed rail will work whether or not we have room temperature superconductors over there in California. But for civilizations that have an effective infrastructure process, this could make your trains much faster.
Yeah, the laws of physics have nothing against the dysfunction of California's environmental review process.
Unfortunately, yeah.
What else should we be talking about that, or stuff that people aren't observing, right? Because there's a lot of chatter about this stuff and talking heads getting on there. Like you're in the thick of it and you actually have a deep understanding of the science. Like what is the most interesting thing to you?
Something that's very interesting is how much a certain equity markets have moved based on some of this information. So there's a stock, American Superconducting Company, that was maybe mostly retail trade flows, but moved by hundreds of millions of dollars of market cap on the superconducting news. I don't know how deep the market was, but you could potentially make a lot of money on public equities markets. There's been some talk around private prediction markets like Manifold Market or Poly Market that are pretty niche, I think, and there's a lot of first-time users there, so it's tough to know how well calibrated their prediction, which is I think around 30% is right now. But to see like huge baskets of public equities move by hundreds of millions of dollars means there are some smart people, trading these stocks that maybe know more than us or maybe don't. And that's, I think, wildly under discussed right now. Is there's a lot of speculation, but like, where's the smart money moving? Could be a early signal.
Yeah, I would caution to say that maybe the smart money is the money moving in, but I think don't underestimate the power of retail and memes to move stocks.
That's totally true. It could just be all Robinhood YOLOs or something in AMSC.
And so maybe just to close off, you mentioned that this is probably, if true, right, 10%, but from an expected value standpoint, like 10% for something so significant. What have we had in the last 100 years in physics, like relative to something like this that are kind of on the same order of magnitude? Obviously, the Oppenheimer movie coming out right at the same time as this is you couldn't write a better script. So maybe walk us through some of the other major breakthroughs in physics that this, if true, would be on par with.
Yeah, what's interesting about this discovery compared to other physics discovery is kind of how niche it is in the scope of physics. So 100 years ago, when we had this kind of golden age of modern physics, we first understood all of quantum mechanics, particle physics, some very complicated stuff that we researched and really discovered for this first time. These were a very foundational understanding of how our world works and really reconstituted our whole stack of how nature works and its properties. This thing is like, we know we can probably have a superconductor that works at room temperature. We just don't really know what it'll look like or like what the exact arrangement of atoms would be to make this thing work. No theory rules it out. Everyone thinks that there probably is something out there that would superconduct at room temperature, but it is kind of like an engineering problem of like, let's just try a bunch of different things and see what works. So from a physics perspective, there's a lot of we don't understand just because these crystals are so complicated and how the electrons flow through them, what they look like and everything. And that's all pretty, I think, useful research, but it's not as foundational as I think some of the big other discoveries we've had, whether it's, the foundations of quantum mechanics, the photoelectric effect, which spun off a lot of this, Einstein's seminal paper in 1905. Or I would probably, as I said before, compare it to like the invention of the transistor, which is, I think, a really important physics discovery in how you can make a semiconductor flip a gate to allow current to flow through it, with super precise control. It's a really interesting, I think, applied physics engineering discovery with a huge impact on the world. And look around us, everything we use has semiconductors in it. They're whatever it's talking about these days. So I think superconductors are likely to be on a similar scale of impact as something like the transistor.
So first we get talking rocks, and then we get floating rocks.
Yeah, first we made the rocks think, and now they're going to float. And we'll see where we go from there.
We wanted flying cars, but we got talking and floating rocks.
Exactly.
In closing here, take one or two of these questions, or feel free to take both. A couple things. You're saying we need to think bigger when it comes to physics. Like we need to be more ambitious. One, say, why do you think we've gotten less ambitious over the past few decades in physics? Like what's held us up? And two, what is sort of your request for ambition in the sense of like, where should we be looking to make more discoveries, or what have we not yet talked about as it hopes to what you hope for the future there?
Yeah, there was a survey that came out like 6 months ago or so in the United Kingdom of scientific researchers where it asked, what do you think is the most important problem you could be working on? And are you working on it? And I think it was like 5% of people said they were working on it. And that's tragic. Like, the brilliant best minds of our generation are doing something other than what they think is the most impactful. The famous quote, if you show me the incentive, I'll show you the outcome. I think, unfortunately, a lot of our research systems reward a lot of incremental progress that builds on the works of others. And it's really hard to take major risks and have a huge swing that's super outside of the mainstream. You're unlikely to get funding, you're unlikely to get tenure or appointed positions at universities. And so, in some sense, that's why I think Lee and Kim, working in a garage outside of Seoul is a really interesting wake up call to the world of researchers that you should try crazy things like go outside the mainstream, do something crazy. As venture capitalists, I'm sure you guys know you have a power law distribution of outcomes, and it's easy to take the safe bets a lot of the times, especially when your livelihood depends on it. But it's worth applying all of our work to what we think is the most impactful, most important things we can work on. And who am I to tell physicists what to work on? But I think it's always a helpful kick for each of us to think, what is the most important thing I could be doing, and am I doing it?
I was just going to say that is like Silicon Valley, right? Like if you just look at the most successful people in Silicon Valley, they tend to be really good at, I'm going to work on this one thing. I'm obsessed with it. I don't care if people care. And there's a funding mechanism for those people. And so I wonder how we can shift some of that. And I mentioned before is you have a lot of these billionaires who've made a lot of money doing a very applied thing within the world of bits, but I think have, increasing interest in longevity. Patrick Collison has the Arc Institute. So I'm optimistic that maybe the kind of meme from the superconductor LK-99 Twitter drama is going to spark some interest in people saying, I have an infinitely long time horizon.
Yeah. Let's do a superconducting Manhattan project. Like, it should be out there, right? Just go find it.
That's an inspiring note to end on. Alex, thanks so much for coming on Moment of Zen.
Thanks so much for having me, you guys. I encourage you to check out Common Coffee, which is I do with my day job. We have try to make the world's best coffee really convenient, but it was great talking to you about superconductors.
I'm a customer. I love it. It's in the freezer. Boom, put it in. It tastes great.
Awesome.
Yeah, and I would just say this is the moment of Zen I learned the most on. So really, really appreciate you coming on.
Thanks so much. All right. Appreciate you guys. Have a good one.